The third section of our chapter takes us to looking at the difference between physical changes and chemical changes. So we know the difference between physical properties and chemical properties at this point. Physical properties are those properties that we use to describe something. It may be a measurement, it may be about its appearance, but remember they are properties that don't cause a change to the substance that we're dealing with. And chemical properties are only able to be seen based on their ability to change. So that's related to chemical change that we'll get to in a minute. So let's start with physical changes. What are some of the changes that can happen to a substance and have it be a physical change? So we start with the question, then why is getting a haircut an example of a physical change? Well, a physical change is a change of matter from one form to another without a change in the chemical properties. In other words, we haven't changed what the substance is. So its identity is still the same. It may appear a little different. It may even change its state from one form to another, but it isn't changing its identity. So some examples of physical changes then: cutting, like cutting your hair; crushing, maybe you take a mortar and pestle and you grind up a tablet or something. That's crushing. Reshaping, like Play-Doh or silly putty; and changing state. And we'll talk more about changing state. So that means dissolving is a physical change. And for some reason, that one is always a sticker for a lot of my students. Dissolving. So when you stir sugar into hot coffee, for example, the sugar looks like it has disappeared. And so a lot of people think that means that the sugar has become part of the coffee, that it's gone. But in reality, the little tiny sugar crystals have been broken down into little tiny, tiny, tiny molecules of sugar. They're so small that we can't see them anymore. And so it has become a coffee and sugar solution, a mixture, a homogeneous mixture, but it hasn't turned into something else. We could prove that because we could get the sugar back. If we allowed the water to evaporate, or we made that happen very quickly, maybe by boiling it off, at the end, we would be able to get the sugar crystals back out of the coffee. We'd also get some coffee grounds as well, but I think you kind of get the idea here. So if you look at it in just plain old water, you can see from the picture here that these yellow spheres over here represent a sugar molecule all nicely packed together. And these little tiny blue spheres here represent the water molecules. What happens when sugar dissolves is these little water molecules kind of work their way in between those sugar molecules and surround it, and then pull those sugar molecules away from the bigger group, away from the crystal. And eventually, all of the big crystal is broken down into individual molecules, and therefore we won't be able to see them anymore because we can't see those molecules. Now, changes of state are those changes between the states of matter, like solid, liquid, and gas. So I want you to be able to identify what those changes of state are. So if you think about the easiest one, it would be things we're really familiar with, right? If we start with a solid and we add some energy to it, probably in the form of heat, we can cause that solid to turn into a liquid. The reason it happens is that added energy causes these particles to start moving apart from each other and wiggling around, and that allows them then to become a liquid. Now, the opposite then of melting is freezing. Again, one we already know. But if we take some of the energy away. Usually that happens as a temperature drop occurs. Energy is given off then from the liquid. The particles slow down and they start to clump together and get organized into crystals, and we get solid ice, and that's what freezing is. So melting and freezing are opposites of each other, and melting is the one that requires the input of energy. We're also pretty familiar with a liquid and gas state of matter change. If a liquid gains enough energy that those little particles move faster and faster, sorry about that, I must have bumped it. Those little particles move faster and faster, they actually will break free from each other and turn into a gas. So that is like the liquid water that turns into steam. That's evaporation. As those particles slow down, often because they come in contact with something that is a colder temperature, those particles clump back together again and go back to liquid form. That's condensation. When you shower, you notice condensation on the mirror in the bathroom. So the liquid water that is coming out of the shower head, if it's hot enough, will have some evaporation and form steam in the bathroom. When that steam hits the colder mirror, then those particles slow down and clump together and condense back into a liquid. So I think that's one we're pretty familiar with. The two that we are less familiar with, though I'm pretty sure you learn about them in junior high, is the concept of sublimation and deposition. Okay? So if we start with a solid and we add enough energy that those particles can go directly from solid to gas, skipping the liquid phase, then we have sublimation. Now, I think sublimation is a little less familiar to us, but I think you'll be surprised. You've seen it before. If you've ever seen dry ice, it looks like it's making kind of a fog. That is frozen carbon dioxide, so solid carbon dioxide. And those particles move so fast, they don't even go to liquid, they go straight to gas and make that foggy appearance of gaseous carbon dioxide. That's sublimation. You may even, without realizing, have seen this in the springtime. Have you ever noticed that sometimes in the spring we have big piles of snow, and rather than seeing it melting underneath the pile of snow, it just gets smaller? The whole pile just seems to get smaller, even though there is no puddle developing at the base of the pile. That's sublimation also. This happens with ice cubes in the freezer too. If you make a tray of ice and you leave it sit for a really long time, eventually when you pull that ice tray out, you'll notice that those little compartments in the tray aren't even filled with the ice cubes anymore. The ice cubes in them are much smaller because of sublimation. The opposite of sublimation is deposition. The key part for me remembering that one is to look at the beginning of the word. To me, it looks like deposit. So if I can think about these gas particles slowing down and depositing on something, then I can remember that's deposition. So again, we're skipping the liquid phase. We're going straight from gas to solid. This one is one we see every year in the fall when it starts to get cold in the mornings. There's moisture in the air in the form of a gas overnight. And in the morning, as the gas begins to settle, it hits the cold windshield on your car and it turns straight into the frost that you see on the car. That's deposition. So believe it or not, we've seen some of these things in our everyday lives. So in your packet, I believe they ask you to label a diagram like this, and they ask you also to highlight the ones that involve an increase in energy. So anytime we're going to make the particles move faster, we're increasing energy. So solid particles are the slowest particles, right? Liquids are somewhere in the middle. Gas particles are moving the fastest. So if we go from solid to liquid, they'd have to gain energy. So melting requires energy input. Liquid to gas, they'd have to gain energy again. So evaporation requires energy input. And to go from solid directly to a gas in the form of sublimation is also going to require the input of energy. So those are all physical changes. Then we have chemical changes. Remember, chemical changes are related to the chemical properties of the substance. So they start with this question: why is baking bread an example of a chemical change? Well, let's think about what a chemical change is then. A chemical change is a change that occurs when one or more substances changes into entirely new substances with different properties. So in other words, we're looking at something that has resulted from a chemical reaction. The end product is something new and different than what we started with. Now, some students would argue, well, isn't liquid water different than solid ice? Well, yes and no. It's a different state of matter, but it's not a new substance. It's still water. Whether the water is in solid form or in liquid form doesn't matter. It's still water, and so that's why it's not a chemical change. What we're talking about here is to turn completely into something else. So how do we know when a chemical change is occurring? Well, some of it is you just become familiar with it, but there are signs that can help you to begin to realize when a chemical change is occurring. Not all of these are a perfect sign of a chemical change, but the more of them that you see at the same time, the more likely it is to be a chemical change. So color changes, that's a chemical change usually. So if we take a look at the example here on the left, they show leaves changing color in the fall as the pigments from the leaves change, then the color of the leaves change as well. That's an example of a chemical change. If you take a look at the middle picture, they're showing like an Alka-Seltzer tablet or something in some water. This would also happen like with baking soda being added to vinegar. We see bubbling. Now, bubbling can be the sign of a chemical change because it means a gas is being produced or given off. But be careful, because bringing something to a boil causes bubbles as well, and that is just a physical change, not a chemical change. So sometimes it's hard to use this one as a sign of a chemical change, but there are other things that could be happening at the same time that may confirm your prediction. The one on the right also is an example of the Statue of Liberty. Originally, the Statue of Liberty as a copper statue would have been that kind of orangish brown color, but over time, chemical reactions occur, and it causes kind of a grayish green buildup of copper oxides on the outside of the statue, and that's why copper looks this greenish color. So that also is a sign of a chemical reaction. So we should probably jot down some signs to help us, right? So things that we know in our everyday lives that are examples of chemical change. If something burns, we get something new out of it. If rusting occurs, when we eat something and our body breaks down that food, that's a chemical change called digestion. Decomposing things. If you leave a banana peel or an apple lay out, you know that it breaks down. You can have a compost pile where you pile up all the leaves and the grass clippings and stuff, and over time that breaks down. So decomposing is another everyday example of a chemical change. So what are some things that we can see happening or observe that can help us to guess whether we're talking about a chemical change or not? So some examples that we already mentioned: a change of color, fizzing, so that's a production of a gas causing bubbles, right? Oftentimes, bubbles, because they're a gas, bring with them an odor, some kind of smell. We may get the production of heat, or sound or light. So any kind of energy change can be a sign of a chemical reaction. Now, this is the substances themselves giving off heat, not the addition of heat, like putting something on the stove or in the oven or even in the microwave. Okay, so what we're talking about here is